Okay, welcome to part 2 of the video on section 3.4. So we were looking at this linear system. Here's our real valued matrix A. But when we tried to find the eigenvalues, we discovered that the eigenvalues were complex. Okay. So there were two eigenvalues, -1 plus 3i and -1 minus 3i. Now what we're going to do in this video is we're going to put together an eigenvalue and an eigenvector to try to build a complex solution, the same way we've been doing with our real solutions. That's not ultimately what we want. We want to find real solutions to this real problem, okay? But hopefully we're going to be able to sort of pull them out of the complex solution that we build. So I'm going to start by just picking one of the eigenvalues. Turns out I only need to work with one of them, okay? And it doesn't matter which. So I'm just choosing lambda 2. We'll see why in a minute. I'm looking now at the equation a minus lambda 2i times some non-zero vector v, whose components I'll just call v1 and v2. I want that to equal the zero vector. Okay. So when I form a minus lambda 2i, I'm just subtracting this from the entries on the main diagonal. So when I start with 0, I'm going to subtract -1, which means I'm going to add 1. And I'm subtracting a -3i, so a plus 3i. That's actually why I chose the one with the negative imaginary part, because if I subtract it, I'm subtracting a negative, the imaginary part becomes positive. Okay, then we still have just a 5 and a -2. But then from this main diagonal, -2 minus a -1 is going to give me a -1, minus a -3i is a plus 3i. Times v1, v2, and we want that to equal 0, 0. Okay. So the corresponding system of equations is 1 plus 3i times v1 plus 5v2 equals 0. -2v1 plus -1 plus 3i times v2 equals 0. Okay. Now, ordinarily, when we've gotten to this system where we were finding our eigenvector, it was really obvious that we had what we call a dependent system of equations. That is, the two equations were equivalent because one was a multiple of the other. That is true here. It is just not obvious because each one is a complex multiple of the other, and that's a little bit harder to spot. So I'm just going to say I know that this equation is a multiple of this equation because I know that lambda 2 is an eigenvalue, so I know there's a non-zero solution. So I just need to pick one of these equations and solve it. I'm going to solve this one for v1. So -2v1 is going to equal, move this piece over, so it becomes 1 minus 3i times v2. So v1 is going to be, I'm going to just, I'll write it out. 1 minus 3i over -2 times v2. And I'm just going to bump the negative up to the top. So I'm going to write that as -1 plus 3i over 2 times v2. So now I can find myself an eigenvector v, whose components are v1 and v2. I'm going to do that by just making a choice for what v2 is, and then I'll multiply it by that to get v1. I'm going to choose to make v2 2, because that way, if I multiply this by 2, the 2's cancel, and I'm just going to get a -1 plus 3i. So that is my complex eigenvector that goes with this complex eigenvalue. I will leave it to you, if you want some practice just working with complex arithmetic, to say, if I multiply this matrix by this vector, I should get this number times this vector. Up to you if you want to verify that, but it certainly is true. All right, so now, while I'm erasing the board, I will remind you that we can build a solution by taking e to our eigenvalue times t, and then multiplying by our eigenvector. So I'm going to go ahead and find a complex solution to this differential equation. So I'm going to say y is equal to e to the lambda 2, so -1 minus 3i times t, times my eigenvector, which is -1 plus 3i, 2. That's a complex solution. I'm going to just do some simplifying of it now. Okay. So, notice with this exponential, this is e to the negative t minus 3it, and then times negative 1 plus 3i, 2. Okay. So I just distributed the t here. So here I've got a real part and then the imaginary part. So I'm going to just split that up. I'm going to say that's the same as e to the negative t times e to the negative 3it. And then still times my eigenvector. Okay. Now I can do that because if I look at this, if I'm multiplying things with the same base, I would just add the exponents. And here, that was just adding the exponents. So I write it as e to the real part times e to the imaginary part times I. Okay, but now I can use Euler's formula for this part. Notice I had to separate out the imaginary part times I from the real part before I could apply Euler's formula. But now I can say that's e to the negative t times, this is going to be cosine of negative 3t plus I times sine of negative 3t. And then all of that still gets multiplied by my lovely eigenvector here, which is just hanging out for the time being. Okay. Now, to make my life a little bit simpler, I'm going to use the fact that cosine is an odd function. That means that cosine of the opposite of theta is the same as cosine of theta. So if I've got a negative input, I can just ignore the negative sign. Sine is an, did I say cosine was odd? It's even. Cosine is even. Sine is odd. Sine of negative theta is the opposite of sine of theta. So here when I have a negative input, if I want, I can pull that negative sign out. Okay. So this is the same as e to the negative t times cosine of 3t minus I times sine of 3t. That just makes it a little bit nicer because it makes the argument of my trig functions not have a negative sign in it. And then we're still multiplying this by our eigenvector, which was negative 1 plus 3i, 2. Now, what I'm going to do is I'm going to write out the components. So I'm scaling this complex vector by this complex function. That means I'm scaling each component by that. Okay. So, when I do that, on the top, I'm going to have e to the negative t times cosine 3t minus I sine 3t times negative 1 plus 3i. And then on bottom, it's a little bit simpler because I'm really just distributing a 2. So I think on the bottom, I'm going to go ahead and distribute the 2 and the e to the negative t to each part. So I'm going to have 2 e to the negative t cosine 3t minus 2 e to the negative t sine of 3t times an I. Sorry, I dropped the I. Okay, so notice on the bottom I've got this neatly written as a real part plus I times an imaginary part. That's how I'd like to get the top written as well. So I'm going to just FOIL out the stuff that I have there. So coming up to this part of the board, we're going to have, I'm going to, for the time being, just keep that e to the negative t off to the side and FOIL this out. So I'm going to get negative cosine of 3t, let's see, plus 3i times cosine of 3t, minus a negative, so plus I times sine 3t, and then minus 3i squared sine 3t. And what is I squared? Why, yes, I think I hear somebody saying I squared is actually a negative 1. So this is negative 3 times negative 1. It just becomes plus 3 sine of 3t. Then on bottom I had my 2e to the negative t cosine 3t minus I times 2e to the negative t sine of 3t. Okay. So what I'm going to do is I'm going to now split the top up into its real and its imaginary parts. So I'm going to go ahead and distribute the e to the negative t, but I'm going to consolidate my real and my imaginary parts. So I've got e to the negative t times that's real, so negative cosine 3t. That's imaginary, but this becomes real because that I squared was a negative 1. So this is plus 3 sine 3t plus I times e to the negative t times, let's see, this part was imaginary, so I've got 3 cosine 3t. I just put that I in the front, and then plus sine 3t. Okay. And then on bottom I've got 2e to the negative t cosine 3t minus I times 2e to the negative t sine of 3t. All right, so within each component, I've written it as real part plus I times imaginary part, or real part minus I times imaginary part. Okay, excellent. I'm going to now do that at the vector level. I'm going to write this entire vector as the sum of a real valued vector function plus I times another real valued function. So I'm going to write y as I'm just going to take one vector as being my real parts. So e to the negative t times negative cosine of 3t. This didn't dry very well. Okay, negative cosine of 3t plus 3 sine of 3t. And then here, 2e to the negative t cosine of 3t. Plus I, so I'm just going to factor out the I, that is a complex scalar. And the rules for scalar multiplication work the same whether it's a real or a complex scalar. So it's I times e to the negative t, 3 cosine 3t plus sine 3t. And then on bottom, don't forget that negative, minus 2e to the negative t sine of 3t. Sorry, y is a vector. I can call this the real part of my solution y, and I can call this the imaginary part of things. But again, just like with complex numbers, the imaginary part is real. It's the coefficient by which we're scaling the imaginary number I. So this is a real valued vector function. This is another real valued vector function. So for one complex solution, notice there are two real vectors that I can associate with that one solution. And wouldn't it be nice if this and this were solutions to the original differential equation? That is actually the case. I'm going to leave it as an exercise for you to verify that that works for these particular examples. When we come back, we're going to prove that in general, if you have a complex solution to a real valued differential system, like linear system like this, then the real part and the imaginary part will both be real solutions to that. Come back, that's going to be exciting.